Hello, everyone. Welcome to the 7th Railway Talk for the UEEIV. This will be on ballastless track, so slab track technology. We have two speakers here today. Our first speaker will be Vlad Metaxa. We'll be looking at slab track explained through recent application processes. And then we have Stefan Vonbun from Rhomberg Sersa, who will be looking at superstructure upgrade during short track possessions. So it'll be, and we'll have Vlad go first with his presentation and then questions afterwards. So if you'd like to put your questions in the chat, and then I will ask the questions to Vlad, and you can get your answers, and then Stefan will do his presentation and we'll do questions at the end too. Okay, if everyone's ready, we will go straight in. Vlad, do you want to start with your presentation?
Yes, thank you very much. Hello, everybody. I will share my screen. Maddie, please let me know if everything goes well with it.
Yeah, all good, can see it.
Okay, perfect. So thank you very much for this opportunity to present the slab track explained through recent application projects that we delivered along the time. Today, I will talk about a little bit about the company and myself. The next topic will be when and why slab track as a solution. Then the slab track application implementation through projects, design consideration for optimal approach, and operation and maintenance aspects. So my name is Vlad Metaxa. As I was introduced, I'm an engineering lead in our Porr Slab Track International Department. I'm based in Qatar, and yeah, I'm working in Porr since 17 years now. The last 10 years were focused only on slab track technology, especially our system. However, today I will talk broad about other systems as well. About Porr, we have around 155 years of experience. Of course, we started quite a long time ago the implementation of railway systems. Here you can see pictures from 1928 of the tram line in Vienna from our archive picture. So why we are talking about railway expertise at Porr? It represents one of the core competencies in Porr. We have extensive experience in execution on demanded domestic and international projects. We delivered until up-to-date high-speed railway tracks, mixed traffic, freight, metros, and trams. So practically, we covered all the different type of tracks. We have over 1,000 kilometers of slab track delivered and installed in Europe, Asia, Australia with our technology. Of course, we are trying to promote this, but sometimes other projects, they have different requirements, and therefore we try to go along with that. And we did install the railway on bridges, earthworks, and in tunnels. So practically, we face all different challenges that railway can give to the contractors, to the clients, to employers, and so on. So all the stakeholders involved in this. As type of railway tracks, I just want to touch brief on this aspect. Because normally in ballasted track, the ballast substructure, it's being an elastic environment. Practically, it's taking a lot of the dynamics of the trains and dissipated to the sub-base layers. And the fastening system, it's more or less a little bit not as much as, let's say, stressed under this type of loads. While in the ballastless track system, the structure practically it's taking has less elasticity, and therefore the fastening system it's more, let's say, exposed. However, this along the years and along the technology development proved that the ballastless track systems are much more durable and they are much more reliable during operation times. So this is one of the most important aspects that needs to be mentioned here. In terms of type of slab track, there are different systems on the market. So always the specifications more or less are done openly for all the different types of systems to be implemented. Here I will touch on the main categories that, of course, we are facing and installing. There are the compact system, which are the monolith system, cast in situ sleeper, which is the most, let's say, known, the REDA 2000 system. Then we have the base plate system, which are practically fasteners that are installed directly on the concrete base. Which there are several suppliers like Coyle and Roll that they have different models for this type of track. Then we have the block systems, which is also a sort of compact system, but it's a little bit more proprietary, like the ZDF and LVP with the booted sleeper systems. Then we have the embedded rail systems like Edilon, Cedra, and Pandrol, where practically the rail is embedded in all kind of specific materials, proprietary systems to hold the rail in position to the required geometry. And however, these are more or less systems that are suitable for certain type of tracks. And then we have the prefabricated slab track systems like J-Slab, the Max Bergel system, Porr slab track system, and there are also other systems in Europe and in Asia that are more or less from this category, taking part from this category. I will focus now the discussion on the when it's required or when it's suitable to apply the slab track system. Usually, and I think the most important or the project that require mostly this type of track. Of course, there are authorities and networks that are operating high-speed trains on ballasted track. I'm not saying that it's not existing, but the slab track technology proved along the years that it's much suitable for this kind of operational tracks for high speed due to the high performance requirements, high accuracy that it's required. And we faced also projects when the rehabilitation and electrification with limited tunnel clearance were required to be done. And therefore, the slab track technology was the most suitable type of track to be installed in such areas. And of course, always now more and more we are facing projects which present difficult access areas. And therefore, these slab track technologies are the most appropriate to be executed. Why? To install slab track, it's because the maintenance it's reduced. The requirements for maintenance, you don't affect the revenue times. Of course, different systems they present different challenges. However, there are certain systems that they have additional benefits. The long life cycle, high availability of the track and the revenue times, high track precisions, which is actually having secondary effects like reduction of the noise and vibration emission of the track, lower effects on the wheel of the trains and so on. And more we face the requirements for trafficability with emergency equipment in different, let's say, areas with difficult access like bridges and tunnels. So this is a major advantage that the slab track has compared especially with the ballasted track. Talking about projects and how we implemented this technology, the slab track technology in the current or delivered projects. One of the example is the high speed in Germany, where we delivered VD8 project for operational speed of 300 kilometers per hour. The entire line on bridges at grade and in tunnels, it's completely done with slab track system. And as you can see out of the picture, for the pocket tracks or areas that are not as exposed to the daily traffic, they can be executed in ballast track in order to, let's say, optimize the costs for the project delivery. But overall, for the main line, definitely the choice was to go with the full ballastless system in order to avoid this kind of interruptions and to have full availability of the track. Another example is the high performance line in Austria. Here as well, usually the slab track is installed in tunnels and bridges. And areas with more challenging accesses. The operating speed in Austria is 250 kilometers per hour. And there is another criteria that it's applied for the ballastless system in Austria installed in tunnels over 500 meters or bridges and in short open sections between two tunnels. So if you have two tunnels that are one beside the other, instead of doing transitions and impose or add a weak point in the track, which can present the maintenance requirements during operation, it's decided now to go throughout with the ballastless system. Another example of delivered project with ballastless system is the King's Cross gasworks tunnel in London. This tunnel was decommissioned in 1970s. And it was identified as a possible and to add capacity to the King's Cross. And therefore, the ballastless system chosen for this location was the Porr slab track system, which had integrated resilient material in order to act as also to mitigate the noise and vibration emission from the track. And by reducing the thickness of the track and the width, they could install two tracks and also the overhead line above. So this is another example how the slab track technology can cope in these difficult areas with difficult access. Another example, and I like always this cross-section to show the comparison between the ballasted track on the left and the slab track on the right, is the Rhomberg tunnel. And this is a practice in Austria because the structure gauge, by inserting the catenary line, had to be increased and the thickness of the track reduced. And here you can see clearly how much space you gain by introducing such slab track technology, beside the fact that you can treat much better during such a rehabilitation activity, the drainage system, the cable troughs, and all the other components of the tunnel, the MEDs and so on, in order to optimize the traffic. Another project that we delivered was a greenfield project. So this is another application. Of course, this is the ideal case. Yeah, Metro Doha was one of the largest metro project that we execute. Here we had 165 kilometers of underground elevated at grade track. And of course, again, the technology of slab track proved that we could deliver such a large-scale project within 3 years in order compared to a system, a ballasted system, for example. It would have been impossible to do that. So therefore, this was proving again that the slab track technology is much more suitable for this kind of application. And in this project, we implemented also around 109 scissor and crossings with various geometries. And this was executed as well in slab track. So here you have an example. Of course, these are larger turnouts that are suitable for high speed, in instance. But you can see that you can do all the prefabrication of the track off site in advance to installation. And then during installation, you just bring the prefabricated elements and you install them. And what is important for this kind of areas is the accuracy, because working in ballastless track in concrete, the accuracy of the track is very high, and therefore the human error or the installation errors on site are much reduced, and in this way you can obtain a good track quality. The same applies for rail extension devices on slab track that are necessary for bridges where we have expansion joints that are having large movements during the temperature changes. And the same we were with the experience we got along the projects delivered. We now definitely look always to go with ballastless solutions for these areas, since are much more stable and present less headaches during operation and maintenance. The design consideration for optimal approach, longevity and cost effectiveness, what we are facing usually is that the procurement schedule and the impact of the design integration are, let's say, faced by the contractors. Yeah, because usually the design starts bottom up, or the procurement, which is normal. You need a structure underneath to be able to build a track. However, if you don't have the design of the track desired to be implemented, then this represents can represent an interface issue during design and construction. So we always encourage the authorities and the employers to consider engaging the design track designer early in the process in order to avoid all the interfacing issues that you can face during construction. What happens if you engage the designer? You will be able to have a cost-effective solution because you can optimize the bridges, you can optimize the tunnels, and so on. The life cycle, you will have a long life cycle if you consider properly the track structure interaction, and you will have an optimized solution for the respective line. And of course, you mitigate all the project execution risks by doing this. Of course, you can have a holistic approach if you do that, and you can reduce the dead load of the track formation. You have cost saving in the bridge structure design, and you can have reduced quantities for the track especially. Yeah, that practically are just generating costs due to longer installation times and longer, let's say, quantities, higher quantities that needs to be installed. The advantages for tunnels are the cost savings in tunnel section, considering the reduced thickness of the track. So the ballastless requires less space provision, and of course, reduced concrete quantities. This is not really impacting the clients, but what gives brings a benefit to the employers, the authorities, is that you can get more clearance in the tunnel for installation on all different types of equipments that are required to be installed. The slab track operation and maintenance, definitely along the years, it was proven that it's much more reliable. The availability of the track is higher. The track precision over lifetime, it's maintained. So practically having a concrete structure, you don't require so much maintenance activities to do. Therefore, the costs for maintenance are reduced. and the overall lifetime generates a reduced cost for the design life period. Here we have a track alignment quality check between, on the left side you have the ballasted track, and on the right side you have the slab track, and you can see the quality of the track. It's completely different. So this is done after several years of operation, and of course the readings are, let's say, for the ballasted track preventative, they will need to do some tamping activities in order to realign the track. However, for the slab track, it's not required, and the operation can continue as is. Of course, visual inspections and now videos or whatever technologies are required to be done, just to be sure that everything is fine. But in principle, there should not be any risk on that. The cost between the ballast and ballastless, we did several assumptions, exercises for different clients. The break even usually it's somewhere between 15 to 20 years between the investment cost of the ballast to investment cost of the ballastless. And of course, depending on the type of ballastless system, you then have also additional advantages, but I will not go into that detail at the moment. However, what I want to say, always it's difficult to beat the ballast price per linear meter during construction. However, if somebody is looking long-term investment, definitely the ballastless system will always be much more reliable and much more cheaper compared to a ballasted system. Not talking about environmental impacts nowadays and the heavy equipment that you require to maintain the ballast track. As a summary, of the slab track, it's long-lasting, effective investment. So for the clients, I think this should be a prime consideration in their assumption. I have to say, for large networks, the track, it's more or less, let's say, it's a system-wide solution. So therefore, I think for the authority should be good to consider always the track as a whole package, as a standalone package, and the engagement of the design should be earlier together with the civil contractors in order to save and have lower life cycle costs. And of course, overall, the high availability of the track and no impact on revenue hours. This is, I think, a clear message that the slab track generally it's providing to the authorities and to the operators. So thank you very much. I try to keep it very short so I don't get bored anybody. And of course, we will share the presentation, and here you can see some links to different videos and different additional information. So be invited to visit them and check. If there are any questions, I'm happy to answer. Maybe I think you will support me in that. And I hope you enjoyed the presentation.
Thank you, Vlad. That was great. Really interesting presentation about slab track. We've got some questions and hands up as well. So we will, if anyone wants to put their questions in the chat, or Charlotte, if we can unmute them for people to ask their questions, that'd be great. I'll start with the Q&A questions. We have one saying, considering MTTR mean time to repair slab track, have any studies been carried out or not? So I'm assuming kind of what's the mean time
for metro track, or
for mean time to repair slab track?
Yes, it depends on the type of the track that it's installed. In principle, always it depends on the type of track that initially was installed and access points for such a track. We have done studies, for example, for replacement of the ballasted track with slab track. So this we are currently having several authorities that they require this to us to study, and we are working on it. However, we have also the requirements in networks where the ballastless system got to the maturity to look in areas that are affected and they need replacement. So we have different projects with this kind of requirements. Yes.
Cool, thank you. Mario, did you have a question?
Yes, hello, colleagues. I'm Mario Galaba from Railway Infrastructure, Bulgaria. And have one question. You know that in Bulgaria we make so big buildings of railway infrastructure according to European corridors, and some of tunnels must be designed with slab railway slab track. And my question is some remarks, some problems according to transition zone between conventional track to the slab track, because I think that is the most important point between these two decisions for railway track. Thank you.
Yes, so to address transitions, in order to design a proper transition, you need to consider properly the operational speed of the train, the operational load, and especially I think also another important aspect is the fatigue to the transition. What we are usually doing, we are having the transition is starting on the ballastless track, and then within the ballasted track, then we'll have sleepers with different fastening system with different thickness in order to have a smooth transition. We are also depending on the type of structure, because sometimes we have not only the track difference, let's say the different type of tracks, but we have also different type of structures which are adding additional challenges to the transitions. So in that case, you might need some extra rail or extra provisions for rigidity of the track between the two. However, as I said, in Austria, for example, the clear consideration for two tunnels in proximity will be to go through ballasted track. Otherwise, you will have transitions. So we can treat that, and it is possible to have a solution that requires less maintenance or doesn't require too much maintenance. Yeah, of course, for the ballasted area, you need something, but for the slab track, it's not really required.
Does that answer your question, Mario?
Thank you. Thank you.
Yeah, great. Thanks, Vlad. We'll keep going as there's lots of questions coming in now. Next one we've got is whether any special aspects covered in the design for a transition zone, which is tunnel approach as well as bridge approach, or bridge starting from tunnel approach, which I think you may have just covered actually in your talking about the transition. So we've covered that.
Just to add on for the bridges, definitely we will need to look also in the structure behavior and to add on to the study the track structure interaction. So it's a little bit more complex, but as I said, it's doable. I mean, it's not a problem to do that.
Cool. Then next one is whether a slab track earthing system design vary depending on the type of power supply, either third rail or overhead catenary system.
Yes, it is different, and we do have different solutions for this type of electrification systems on different networks. So,
okay, cool. And the next one, I'll just keep them coming. So how stray current protection system is provided in slab track? Stray.
Yeah, it's similar
Yeah.
question, I think, and stray currents. So as I said, we have first of all, the fastening system is usually much more resistant, first of all, in comparison to ballasted track. However, we are treating the stray currents and the earthing through the slab track, having different solutions. Now it is important to see what type of track is selected. Yeah, because as I said, I can talk for slab track system. I know exactly how we do that. For the other systems, might differ a little bit the approach, but in principle, our technology, for example, having also the separation layer as another isolation layer in the track substructure, brings also additional value to the treatment of such phenomenon.
Cool. Great. Thank you for that. Vlad, can you take away your presentation so it's easier to see the participants?
Sure. Sorry for that.
Then they can see you better too. Really in the spotlight now. Next one from Abigail Cahen. In the high-speed in Germany case study photo, what is the function of the ballast next to the ballastless system? Not on the adjacent track, but alongside the concrete, is the question.
Sorry, in the presentation, the picture I have.
Yeah, maybe it's worth bringing it up again.
Okay, I'll put it back again. Yeah, the reason is that in this particular case, one second to go there. Yeah, so as you can see, the main line is ballastless track, but on the pocket tracks, it's not needed. So here, usually you put in the maintenance equipment along the way, or there are safety requirements for such track, which is not practically operated full time. Yeah, they are operated only in limited time, and therefore the impact of such, and beside this, they are operated with reduced speed. So they are not operated with 300 kilometers per hour. And therefore, the cost for such tracks to do them in ballastless is not really needed, because you can easily or they serve properly being in ballasted tracks. So that's why the choice of the authority in this case.
Okay, Abigail, you have your hand up. You should be able to unmute yourself now if you want to ask a question. Yeah.
I was specifically wondering, not on the adjacent track, but along that center track, there's still ballast along the sides of the track. And I'm wondering what the function of that is, or if it's just sort of left over from previous.
It's in the area of where we have gelidity cycles. So therefore, this is a freezing protection layer. It's set up as a freezing protection layer.
Abigail, does that answer your question?
Oh, yes, thank you.
Cool, thank you. Okay, are you good for more questions, Vlad? We have
sure.
Lots coming in.
I don't know, Stefan, how good is he, but for me, it's okay.
Yeah, Stefan, feel free to come in. Yeah,
it's okay. Let's see, once the numbers are starting to drop in the participants, then we maybe should stop. No, it's fine. Yeah, it's usually we have the other problem, that nobody's asking. So
yeah, this is great. Yeah, we've got lots of people engaging. I'll ask, I think, 3 more, and then we'll move on to Stefan's, and then we can do the rest at the end, because Stefan's presentation might also answer some of these questions. We'll see. So let me just pick one out from Stefan Offenbachia. I hope I pronounce this okay. What is the life expectancy of slab track? In your graph showing the break-even point with ballasted track, it seems to be over 80 years. Is this a reasonable value?
Yes, so for our system, which was initially installed 30 years ago, there were some studies made, and now initially the system was designed for 50 years. However, now it was increased to 80 years without doing anything to the track. So that's why in our comparison with cast in situ solution, the comparison there was ballast track, Porr slab track system, and cast in situ system. As a basis for this increase was this research that was done. And now in new networks that we are designing for, we have the requirement already implemented in India and Australia for 100 years, design life. And for other networks, we are also looking in 120 years. Of course, these are having different impacts on the mixed designs. We are using the concrete cover due to durability and so on, but it is achievable and it is possible to be done. So that kind of approach, it's already implemented to go for more than 50 years.
Wow, good to hear. Cool. Thank you for that. We'll go into the chat and have a look. What have we got? So from Pernell Krams, accepted that ballast track has more advantages compared to ballast. Slab track has more advantages compared to ballasted. As for high speed and accessibility, can slab track be applied and offer similar benefits to heavy haul railway systems?
Yes, we designed and tested the slab. We never implemented because we didn't find a project. We were actually doing it for Middle East, where we designed a system for 32.5 tons XLO, and we tested in Technical University of Munich, and the results were good, and therefore were successful. So therefore, now we are participating currently in a tender where the 32.5 tons XLO, it's in Middle East, so therefore the requirement, it's back, and definitely the system is suitable. And I think the ballastless system for heavy haul, it's one of a great advantage because the fatigue in the ballasted track, it's completely, it's much higher than or let's say that the fatigue result on the ballasted track, it's much higher than you would have on a ballastless system. So I would definitely recommend going in ballastless for that.
Great, thank you for that, Vlad. Last question for now from Thomas Heckhausen. He was wondering about the repairability aspect of slab track compared to ballasted track, e.g. in case of derailment. Are certain types of slab track easier to replace than others?
Yes, it's a good question because usually what we faced, and we had an example in Austria, in which the wagon bogie broke and was dragged on a ballasted track and then entered in a tunnel with ballastless. And obviously the ballasted track, all the sleepers were completely damaged due to the fact that they are pre-tensioned. So in the moment they have an accidental load, they will crack. And on the ballasted track, and it was a heavy case as well, that we had the noise absorber panels installed on the slab track, and the train practically was guided between the rail and this noise absorber panel, and only the support points were damaged. That could be replaced on position. We did not have to remove the slabs. And but talking generally, depending on the system, you need, for example, and I will talk more about settlements. Yeah, for example, if you have a casting solution, you will need to remove everything and rebuild if you cannot cover it in the fastening system. But in the prefabricated modular solutions, it's much easier because you can just lift the elements and regrout underneath. So there are several advantages in different types of ballastless systems as well. But in comparison with ballasted track, definitely the behavior of a ballastless system, it's much more performant and requires less efforts for such in cases of such accidental loads.
Okay, great. Sounds great. We will move on to Stefan's presentation now. I appreciate there's still lots of questions, but that shows that it sparked a lot of interest in the audience. So thank you very much, Vlad, for your presentation, and hope you can be here as well to answer the questions at the end too with Stefan. So on to you, Stefan, talking about superstructures.
Thank you.
Thank you.
You can hear me? Yes?
Yeah, can hear you.
And you can also see my screen, yeah?
Yeah, I can see your screen too.
Thank you. So, yeah, it's a pleasure to be here today. My topic is the one of superstructure upgrade during short track possessions. And as there was already quite a few questions, and Madeleine already mentioned, maybe my presentation can help to alleviate some of the pain in these questions. Let's see about that. If not, I'm happy to answer the questions after the presentation. So very quickly, I'm going to introduce myself. So who is this guy standing here in front of you? I'm Stefan. I'm from Western Austria. It's really beautiful here. We are located in the mountains. I have a technical background. I once learned how machines work. Then I was looking for water in the beautiful country of Jordan. For a while, I stopped railway vibrations and developed some new business areas. And now I'm going full steam ahead with our slab track system IVES and our transition module VTRAS. So next year, I will celebrate my 10-year anniversary in the railway infrastructure business. So let's go ahead. I have a few assumptions why you people, we are now more than, well, we are 100 participants, why you are here, what your interests are. I assume that you are interested in state-of-the-art in railway infrastructure. You are looking for safe and proven solutions, and you want to increase the overall efficiency of your superstructure, including the construction of the superstructure. Since I cannot see you nod, I just assume that I have 3 positives here, and we can move on. I'm here to give you a quick overview of what we do at Rhomberg Sersa, also to connect to people, so you know who to call in case you have issues that might be something that we can solve for you. And also, of course, I think this is a really crucial part, and we just saw that. I'm here for exchanging knowledge and receiving some feedback. So yeah, 2 brief slides about Rhomberg Sersa. We are actually a Swiss/Austrian company. We have around 3,000 employees worldwide, and we work in construction, reconstruction, and maintenance of railway infrastructure. Yeah. So with some of the questions that were asked during the previous talk, we already have a lot of experience because we not only build our own system, we have built almost any slab track system that you can find. Where are we located? We are proudly based in Austria and Switzerland, where we have our headquarters, but we are active in 9 countries and 3 continents, and we have around 100 branches all over those countries. And sometimes we also do project business in countries that are not on this map or not orange in this map, because if it's an interesting project, we will always consider it. Okay, now let's go for the actual, let's say, topic of today. I'm going to talk about IVES, our slab track system, and how it can help to actually build faster and yeah, have some upgrade of tracks in short possessions. The challenges of railway operators and asset managers are quite the same all over the globe in our experience. So one thing is that the topic is that operators are running more trains, and this reduces the time for maintenance and construction. So, for example, consulting engineers like Mr. James Cooper, they have to deal with that, you know. So even in the planning of refurbishment or of a greenfield project, a lot of stuff boils down to construction speed and efficiency. Another topic, and this is more the topic of the track engineers or the route asset managers or whatever they are called in different places. They don't have time for maintenance, but stuff keeps breaking. And that's, for example, the problem of this Sophie Bennett, who is a track engineer somewhere. And don't worry, both the profile pictures and the names are AI generated, so there's no GDPR infringement here, but these are the actual challenges that we see on a daily basis from our clients. And yeah, the railway infrastructure is developing. Also, the challenges are changing. So is Rhomberg Sersa, and that's why we developed our very own system. Because, I mean, Vlad already mentioned quite some different systems. All of the systems have advantages and disadvantages, and there is no one-fits-all solution. But still, we thought that we can bring something to the table by eliminating maybe some flaws of existing systems or combining positive stuff of existing systems and adding some new stuff to it. And still, there is no one-fits-all solution. So this is yet another solution, and I'm going to show you how it works. So we have quite a few building blocks that go into this IVES system. We have a direct fixation fastener, which was co-developed between Vosloo and Rhomberg Sersa. There is a fast-setting grout that plays a crucial role. The IVES blocks, so the actual building blocks in terms of load-bearing and gauge-holding layer. We have shear dowels, yeah, optionally, depends on where we are in the track and if we are in a curve or in the beginning of a tunnel or something. And there's a base layer. And one colleague once put it very nicely, and this kind of also inspired us. Hermann Granik, he's a foreman who has been working for 40 years in the railway business. And he said it's as easy as constructing with Lego to build this system. So I couldn't resist, and I had to build it with Lego, you know. This is also actually very helpful to explain it not only to children, but also to engineers, because it's very hands-on. And so one small anecdote. My presentation looked very differently just, let's say, up until 1.5 hours ago. But a young colleague of mine, Daniel, he was actually working on an animation on some construction sequence simulation and involving our system. And I told him that if he speeds it up and if he can finish it in time, I will change my presentation and I will remove most of the pictures and will use his animation. And yeah, just 1.5 hours ago, he finished it and he handed it over to me. And so now I will explain the next steps via this animation. Yeah. And so you are also now witnessing the world premiere of this simulation. One word about simulating construction sequences. At Rhomberg Sersa, we have found that meticulous planning is really important in ever shorter track possessions. So we are kind of heavily invested both with the resources and time to be at the forefront of simulation before constructing. Yeah. So we look at 4D simulations that don't only include the physical objects moving around, but also include the data behind, like how many meters per hour can you actually build with this or that system? How fast does an excavator move? Yeah. How fast does a truck move? And then we combine this and we check with the actual geometry, for example, of a tunnel, if things can actually be brought in there. And like like this, we really avoid a lot of the problems that can then occur on the construction site. And this is the idea behind doing these simulations. And yeah, I'm just gonna let it run. And this simulation will show the construction steps of our IVES system. Like any model of reality, it's not reality. Yeah, it looks a bit more like a computer game. And the idea is it helps to explain stuff. We have some data behind it, like I said, and that helps us to also estimate construction times. Yeah. So let's just dive into it. You should now see a train going into a tunnel. So this tunnel shall be refurbished. It shall be refurbished from ballasted track to slab track. So the track will be closed for maintenance or for construction. And the rails are first put in. These are the new rails that will be used later. Why do we do that now? Because we can now operate on the existing rails, and this is always faster than using a truck or something later. Yeah. So then the existing track is cut into panels, and then our nice Kirov train comes in and removes the track panels. This is relatively efficient because yeah, it's 18 meters with each move. And then we start removing the ballast. And here you can just imagine, this is not shown, but the ballast is removed, it's put into the truck. And behind the simulation, and we are showing now only excerpts, we of course are calculating how many times does the truck have to go in and out. Yeah. Then the tunnel floor is lowered a little bit, or we make let's say a smooth and even surface. We also clean it. We mill the drainage channel, because there will be water and we don't want to have that in there. We install a drainage pipe, and then we are already going for pavement. We, with our system, usually work with asphalt, yeah, for several reasons. One of the reasons is asphalt is quite fast curing. So only after a few hours, depending on the temperature that you are encountering, you can actually drive over it again, and it's load bearing very quickly. And so this is a nice way of having a base layer very quickly. We install the dowels. Usually inside of a tunnel, they are installed every third element, so every 1.95 meters. And then we are already installing the blocks. Yeah. In this case, this is shown now here with an excavator, and I will show you in a bit how it can also be done. There's different ways of doing this. The fastening systems are then installed. I mean, it's a direct fastening system, so it's not finished yet. We actually have to install the rails and manufacture actual track panel that we can move. This is done here. The track is being aligned like very precisely. Formwork is installed. And then after installing the formwork, we actually pour the fast setting grout into the slots in the fastening system. And that's how everything is put into place, fixed in the perfect position. Yeah, track geometry is enabled and ensured by actual surveyors going through, checking everything. And then in the end, we will tension the rails. We will then weld them together. And last but not least, the track closure is lifted, and the train will come through, and the track is back in operation. And now there will be a few facts about this project. It's a fictitious project. There's a little disclaimer on the bottom. It's a fictional project, but we took all the data from actual construction sites. Yeah, so 450 meters of tunnel, refurbishment from ballasted to slab track. The dismantling of the ballasted track, like we simulated here, would take 6 days, and the installation of our slab track for the whole tunnel would take 14 days. So 20 days of work. And of course, the boundary conditions and the construction time in real projects will always be different. Nevertheless, we have a simulation system that can help us come closer to reality. If we get some data, we can actually look into it and check if this is something that makes sense to do, for example, with this system. Yeah. And so, yeah, IVES was developed for fast construction during ever shorter track possessions. And I'm really glad that, thanks again, Daniel, for finishing the animation. I think it it perfectly explains how we work here. And now I want to continue. And another video, but I'm going to jump through it briefly, quickly. This was the simulation, but there's also reality, because if I only show simulated pictures or simulated videos, you guys will be wondering if anybody ever built this system. And yes, we did that. And this is the, 1 second, I have to remove the sound because my ears are exploding almost. Here. Okay, so this was the project that we did in Germany for doing the operational testing for the network of German railways. Zionberg Tunnel, somewhere in the middle of Germany, I would say. And here you can see the actual track, how it was constructed. This is already the final pictures, or we did a video when everything was finished. But also, we can jump a little bit to the front. We can see here some of the steps that we didn't show in the other animation, for example, the surveying and the adjusting that of course have to take place. Also the grouting process, this was not shown before, but this is how it's done. Now you can imagine a little bit better, because now we have a cross section. The grout fills the whole base plate, and then the system is stable and in place. And that's that in terms of moving pictures. So few more words about what makes construction with IVES fast. One thing is fast setting asphalt. Then we have the high level of prefabrication. We have a very fast curing either cementitious or epoxy grout. Epoxy is of course a lot faster. And there is a high level of automation possible for big projects. And I want to dive a little bit more into that. So we are continuously improving in everything we do, and of course also our construction process. This was the very humble beginnings of first IVES construction, was grouting with a bucket and a funnel. Yeah, I mean, things had to be done, and we found a way. This is not really a state of the art nowadays. So nowadays there is a half automatic mixing and grouting unit. It's a mobile unit that can be put to any construction sites. And this works way better. It's a controlled process, and it's also a lot more fun to work with. And for bigger projects, there is like higher automation possible. Yeah. Talking about automation, we are one of the few companies who have one of these drilling robots that was, I think, recently bought by Fisher Dowels, the big dowel company. We are using one of these currently more in an R&D environment, but also this will be something that we will put to the construction site very soon. What we are already using are gantry cranes. Here, Vlad, little advertisement for Porr. This is a picture from Coyle Tunnel in Austria. But this gantry crane is very versatile, so it can lift anything. And we can also use that one for IVES projects. Also, very interesting, the track adjustment process currently is a quite manual one. This was a bit too slow for us, so we recently developed this track adjustment robot. It's called Rhomberg. And what Rhomberg does is best explained in this short video here. This is a video actually from a construction site in Germany, where we were responsible for track construction. This is the radar system. It was also one of the systems mentioned in Vlad's presentation. And here you can see it works a little bit like a tamping machine. Yeah, it has like this satellite that goes back and forth, and this actually adjusts the track very nicely. And the operators, they only have to put the alignment systems, which are supports underneath, and fix them. Yeah, and this is already so precise that it's almost the final adjustment. Yeah, after this, the surveyor comes, and the cool thing is we are collecting data with this, so the surveyor doesn't start from zero. He will know before going there which area, let's say, is further away from the perfect track alignment than the other one. Yeah. Okay. Few more slides, almost done. We are also working on making our own system more efficient, not just by using machines, but also by reducing the use of material, lowering even the construction height to give more clearance. And one of the things is to lower the asphalt layer. It will be reduced from 150 millimeters to 80 millimeters. And in order to do that, you have to make sure that the lateral track resistance is still okay. Lateral track resistance is given by this type of dowel. Yeah, it's like a 210 millimeter steel pipe. Looks like this. And whether or not this steel pipe holds our track well in place was a question we were asked. So we did some testing. It looked like this. The Technical University of Munich assisted here with great efforts. And I don't have the official test report yet, but I was there, and we passed it like with very high values. So yeah, we are happy about it. And we can reduce the asphalt layer without any problem. There was a question about heavy haul and slab track. IVES has been in track in Branxton. This is in the network of ARTC in Australia since 2017. It's a track with 30 tons axle load, 100 MGT per year. So it amounts to around 800 MGT, 800 million gross tons up until now. So taking the, let's say, equivalent operating time in a European track, or like the equivalent yearly tonnage, it compares to 40 years in a European track, and the system is great. The client is still happy, so it works, and it's a safe thing to use, also in heavy haul. This is the Zierenberg tunnel that I showed the video before, where we did the operational testing with German railways. And you guys know that the railways are, let's say, conservative business for good reason in terms of safety. Yeah, if something is not safe, it's not going to be used in the track. And so Deutsche Bahn, German railways, they have really high requirements when it comes to this. So this is, I think, a good measure of how well a system works. If you can make it there, you can almost make it anywhere. And the general approval is pending, but the final conclusion of the operational testing was, yeah, it works, and it's a good thing. And this makes IVES also one of the newer systems, even though it has been installed since 2017, around that time, because in railway terms, 7 to 8 years is a very short time. Okay, last but not least, what's the added value of IVES as a slab track system? We can actually ensure short track possessions, so high track availability. There's safety through proven long-term performance, as shown by these examples. We have very high precision through prefabrication and our innovative fastening and innovative process. And yeah, it's easy to replace and dismantle, which is also important because at some point, these systems have to be dismantled. And this was also one of the questions from before. And not every system is the same. So yeah, that's it from my side. Thanks a lot. Before I forget it, Rhomberg Sersa is, of course, also present at InnoTrans in 2 weeks. And questions can now be answered as well, but they can also be answered at our stand. There's an actual IVES slab track there, a small one. I mean, 2 blocks. And yeah, I'm happy to receive now the questions, Madeleine, and to answer them. Thank you.
Great. Thank you so much, Stefan. That was brilliant. just seeing like what's already been improved since you started and how there will be improvements going forward and how it's evolving is always great to see. I love seeing stuff like that. So yeah, thank you very much for your presentation. We're going to try and make this Q&A a bit more interactive. So I'm not just asking the questions. So it'd be great to get people to ask their own questions. So we're going to unmute these people that have asked questions, and they should be able to ask them directly to you guys. So I hope you're ready, but we've got lots coming in as well, which is great. Everyone's very excited about Slab track. So I've got the first one, Abtin Habibi. So he's asked a few questions. One is, the slab track system has less elasticity, and due to this, there are much more impact forces in critical speed. How do you handle track train interaction with high impact forces? Like, is this pads and other fastening systems? Kind of, how do you mitigate this?
Okay, so generally the topic of elasticity in track, I think, is very interesting. We have, of course, looked at these topics, and we are using the proven the fastening system from Foslo. That's from the Foslo 300 family. It has a 22.5 kilonewton base plate pad in there. So the resilience actually comes from that, not from the rail pad. Currently, I don't have one lying around here. Usually there's always stuff lying around. But so the topic is, these things are calculated. They are designed and engineered to withstand the forces. And if you use elasticity from, let's say, proven manufacturer, I think there's even some of these people in the call, then you can make sure that this works. Yeah.
Cool. Abtin, I think you can unmute yourself. Does this answer your question? You're here.
Yeah. Okay. In case there's more, like, just drop me an email or something. Yeah.
Yeah, and maybe he'll be at Innertrans to ask you in person. So that is the ideal, right?
Yeah.
Okay. We'll keep going. So, Stephen Barber has a question. Stephen, can you unmute yourself? If not, I will have a look now. No. Here we go. Do you want to try now? Yes.
Sorry, Maddie, I'm trying to do this, but there's so many questions, so I have to pick them out one by one. And
It's okay.
unmute them. But you can all, if you have asked a question, or it's easier if you put your hand up, because then I can spot you right away and then unmute.
Yeah, that's a good
Stephen,
point.
please go ahead.
Okay.
Yes.
Yeah. Well, which one? Which question? I asked two. First
Yeah,
one was about
yeah.
repairing geometry, correcting geometry faults, where you have a say an embankment that subsides, that suffers distortion, earthwork distortion, maybe not failure, but compaction, and how easy it is, and how you correct geometry, the geometry faults that arise from that with a slab track.
Mm-hmm. Okay, thanks, Stephen, for the question. Nice to see you. So one thing is, of course, that we can use adjustment plates. Yeah, I mean shims. Yeah, this goes only so far, as you know. But recently we had actually in the Bregenz track. I hope I'm not giving away too much, but there was something coming from the formation, not having to do anything with our system, where there was a short section where I think due to heavy rainfall and there was like some issues with the, let's say, drainage around. Yeah, the section sunk down, and what we did there, and the results were actually really good. Spoiler alert. We had a subcontractor who injected some resin or something similar, like fast setting something, yeah, magic sauce in there, that slowly but steadily lifted the track there, and we came back into original construction tolerances, plus minus 1 millimeter. And we will do a study about that, and maybe a publication of some sorts, but it will still need some time. But the site engineer who was there, I talked to him lately, and he said they're really happy about it because there was this dip, yeah, and they got rid of it. So this is a very recent experience that we had with that. In case you want to know more, I would have to check back with that guy, and maybe I could also connect you or something like that. Yeah.
Great.
Thank you. Thank you.
Thank you. And did you want to ask your other question?
I'll ask the other
here?
one, which is I used to work for London Underground, as you may know, and I wondered whether Porr or Rhomberg have developed systems that can be installed during hours out of traffic rather than days, because the conventional way of, if we were to put slab track into a tunnel on Network Rail or on Austrian railways, you take the tunnel out of action for maybe a fortnight, a month, 6 weeks, and then or 20 days in your case. But there are some railways where the management is very reluctant to take a tunnel out of action for that long, and therefore want to look at replacing track or upgrading track in maybe 6 or 8 hours at a time, and whether you've thought of solutions for that.
Yes, that's totally our ball game, actually. So the 20 days that I showed, there was like just an example, we also need to improve our simulation skills. So whenever we have a new guy who can actually be motivated to work on that, then that's something we can give them, for example. But no, the topic of ours is totally in the range of possibility. I mentioned that the grout that we use can either be cementitious or epoxy based. So in Australia, for example, we used an epoxy grout because those guys wanted that thing to be available way quicker. And when it comes to the base layer, if we keep to asphalt, which we have done in 90% of the cases until now, but also in the UK, we did one project where it was roller compacted concrete, yeah, and we put the blocks directly on there, and that worked fine. So there you have a really short curing time as well. If you use low temperature asphalt, which is like 20 to 30 degrees lower temperature than regular asphalt, you not only have increased safety for your workers, but also it cools down quicker because the delta to where you actually need to be for it to be hard is lower. Yeah, and so these are examples. We can also we have a case study where we did IVES refurbishment in short stretches of like shifts, yeah, one shift at a time, and then straight away had trains rolling over it in the next shift or during the day. We can use, for example, a temporary fastening systems. We can also actually put the track panels on, like the newly installed track panels before grouting. We can put them on some transfers, for example, wooden beams, yeah, and have that as a preliminary track where you can go, but you probably will go slower, but you don't have to take it out of operation, which is the crucial point. Yeah. So there's stuff like that.
Yeah.
Vlad,
Thank you.
you also want
and to add on that, Stefan, to you, Stefan, we studied as well locations, because it's not only the construction, one of the challenge, it's also the removal of the existing ballast and the contaminated, usually ballast. This is what we are facing, and all the logistics, how you get that material, how you bring the new material, and how you install the track and leave it within hours to be ready for operation. It's always the biggest challenge for this kind of rehabilitation projects. But as Stefan is saying, we see more and more networks requiring this. It's not only London, and definitely it is a market to look at for our companies in this regard. Yeah.
Okay, thank you very much.
Thank you for your question, Stephen. We'll keep going. Mario, you've got your hand up. If everyone else who wants to ask their question can put their hand up, it'll be easier for us to unmute you. But Mario, do you want to ask your question? Or Mario's friend.
We're a company of several colleagues, which are colleagues of Mario Galabov, and we're at one place and we're watching you.
Oh, great.
So my name is Svetlana Ivanova, and like a colleague of Mario Galabov, I work in the National Railway Infrastructure Company. So I'm very interested in maintenance issue. Every producer of slab track system says that the slab track doesn't need any maintenance except of preventive grinding of rails and so on. But when you sell of your system to the infrastructure manager, do you have any recommendations or requirements for activities for preventive maintenance or corrective maintenance? Because somehow when, for example, appear some faults like cracks in concrete and so on, do you have any solutions that you can send to the infrastructure managers that have your systems, slab systems?
So, Stefan, you can address, I can respond.
Yeah, it's okay. Thanks a lot for the question.
Our tasks are very, very close to for the maintenance of the railway track, and we have such an example that always there is a chance to some faults to appear in the track, even in the slab track.
Yes. So I'm just going to jump into it, and then Vlad, you can add, you can say something else. So I mentioned already in my presentation that different systems have different advantages and disadvantages. So maintenance can come in many different shapes and forms. One of the things, let's look at, for example, something that happens quite often, or more often than one would think. If there's a derailment, what do? I know, for example, sometimes it's enough to just grout the shoulders again if we are talking about a slab system. Sometimes you have to remove slabs, so that can be a pain. With our system, you have small blocks that can be removed. That can be an advantage. Yeah, it's not a monolithic system, so there you have to be, let's say, you have to look at these factors as well. Maintainability and also the ability to dismantle even short sections of a track could be something to look at. And our recommendations, of course, are considering, I mean, the grinding, yes, you're right, this is usually something that should be considered, but also then the elastic elements, the rail pads and the base plate pads, they have to undergo a maintenance cycle. And there, since we are not the manufacturer of the elastic elements, we will always take what, for example, people like Getzner will recommend. If they say, so and so many million gross tons are okay for this type of material, and after this you should maybe check and see. Yeah, but you will always in your track measurement readings, you will see quite early, or you could see early if some faults are developing, and then you can take action. Yeah, but I mean, it's different types of maintenance than in ballasted track, and it's true. Also, slab track is not completely maintenance free, but it's fewer maintenance, and you don't need, for example, big ballast tampers or something. Yeah. I hope that helps. And Vlad, please add.
What I would like to add, usually in our practice, we are providing an operation and maintenance manual. That operation and maintenance manual will have the inspection criteria, inspection regime, And as well, in case of, I see you faced topics like cracks. The cracks definitely they have to be monitored, but to a certain extent you don't need to do anything. But if they go over that respective limit, then you might need to do some type of treatments. But again, it's important to identify the reason, so the root cause analysis, why these cracks are occurring, because sometimes it's not the ballastless system, it might be the substructure underneath, the sealed structure or whatever is around. And based on this, then you can, because even you treat it, it still can reoccur. So you want to stop that. And therefore, you need to do a little bit of analysis of the reason. But overall, in our practice and with our system, this is I can say 100% because I did it for several projects. We are providing this O&M manual. And based on this, then the authority can follow up with the inspections during the operation after we hand over the job.
Thank you. Thank you very much.
And if you are in Bulgaria, sorry to interrupt again, but if you are in Bulgaria, we just completed a project in Giurgiu in Romania. It's a 1.5 kilometer bridge over Argeș River. And it's actually, I think from Bulgarian border, it's maybe 1.5 hour drive. So if you are interested to see, we'll be pleased to have you and show you that project and see how the slab track looks like over there. And we can explain you, we have also rail expansion device over there. So it will be interesting to have a visit. My colleague from Romania is also in the call. So we can share later on contacts, and you are most welcome to come and visit.
Thank you for your proposal.
Yeah, thank you.
Great, this all sounds great. Thank you, Stefan and Vlad. I think we'll have 2 more questions as we have many, and just because of time. So Ishmael, you have a couple of questions. You want to pick your most, the one that you want to ask the most. I think you'll be off mute. Otherwise, I can ask one of your questions. Can you hear us? I will ask a question otherwise from him. So Ishmael says, an intriguing discussion so far, which I agree with. He says, one of his questions is, given the challenges associated with transition zones between earthworks and slab track on bridges, what is the most effective design practices for managing dynamic loads and minimizing induced stresses? Vlad or Stefan, do you want to take this, or is this something that a study that's ongoing?
I mean, I remember, but this is pre-Rhomberg Sersa, that in Qatar Metro, there's a Doha Metro, there's a lot of bridges and overpasses and stuff like that. And usually you use shear keys, for example. You can even decouple them elastically, both to reduce stresses into the substructure, but also to remove or reduce vibrations. Generally, I think this is, I mean, this is nothing that we would shy away from, but usually these topics are then dealt with by the design engineer who is given the actual loads and the requirements, and then does a study on that or the calculation. And this is not a topic that is impossible to solve.
Sorry, I missed the question. I was reading in the Q&As, and that's why. And I hear Doha Metro, and I think I can address
you a beer, Vlad.
Is around the most effective design for the transition zones between when you're going onto a bridge within slab track.
And bridges, yes.
Yes.
Yes. So we had the cases in Doha Metro that Stefan was bringing it up. For example, in Red Line South Elevated, we had the trough. Then we had the at-grade section, which was practically the ramp, the trough and the ramp. And then we were up to on the bridges. So the treatments over there, we are always looking to do it in the fastening system with low-to-low fasteners, because we don't want usually, or the first assessment is to avoid adding a rail expansion device. Yeah, rail expansion devices are very good equipments. I'm not saying that are not, but they will require maintenance along the time, the design life. And therefore, we want first to see if we can do it only with the low-to-low fasteners. If we can do that, then it's easy fix, yeah, because we are usually installing fasteners with different colors for the clamps, for example, and then the maintainer later on knows exactly, in case he has a failure somewhere, he knows exactly how to change it, how to which type of material to use, and so on. So it's a very simple and easy way of treating this. But indeed, it is a phenomenon that needs to be treated. You cannot leave it just by itself. And it's yeah, it is a solution for that.
I just put on one slide. Transition zones can be dealt with differently. We have also a solution that is called VTRAS. Yeah, it's a versatile transition module. Here it shows how it can be used to transition from ballasted track to slab track, but it can also be ballasted track to a slab track bridge or something. Yeah, it doesn't. The system doesn't care if it's a bridge or soil underneath. Just to say, yeah, adjusting the stiffness gradually and then reducing the differential settling at the actual jump. Yeah, so where you actually go from slab track or from one track form to the other. Yeah, let's keep it general. You will have differential settling. You want to reduce it, adjust your stiffness, and you will have fewer issues.
Okay, thank you both for that. I think this is a good place to end. I feel this has answered a lot of the questions that were put into the chat. But if you want to maybe put your details or so people can ask you them individually, or if anyone here is going to Intertrans, then you can ask these two in person. But yeah, I just want to say thank you again both for this. Yes, brilliant. Thanks, Stefan. And thank you to everyone that attended. Our next big event for the UEIV is a in-person event in Sofia in Bulgaria. It's the Railway Forum, and we are really looking forward to it. It is looking more general into the future of railway interoperability. As we are a European organization, we are looking at everything, 25 years worth of experience and expertise with innovative strategies. Here we go. And that is on the 8th and 9th of November. So you can use this link to sign up, and we hope to see you there. It should be a great event we have many great speakers coming. So yeah, hope to see you there. And that is it from me. I hope you enjoyed this presentation. I thought it was super interesting. It's great to see new innovations coming into the railway. And yeah, thank you again, Stefan and Vlad, and thank you all.
Thank you.
See you next time. Thank you.
Thank you very much.
Thank you.
Thank
Good
you.
afternoon.